Okay, time to get started. So here's where we were last time. Well, here's where we were about to start last time. We finished talking about equations. We spent a lot of time talking about how to draw pictures, of solution sets to equations, specifically equations that involve three variables, and it makes these three-dimensional pictures, surfaces in particular, in R3. So now I want to talk about how to use those tools in different ways, importantly different ways, to come up with pictures representing functions. So our goal here is not to represent equations. Our goal is to represent functions. Keep in mind, these are different things, right? An equation is a statement that two values, depending on various things, who knows what it might be, are equal. A function is a process. Right, there's a domain and a target, and then a formula that tells you how to take something in the domain and do something to it and result in something at the target. So obviously they're related, but they're different things. So I want to talk about different ways today to generate different kinds of pictures representing functions critically. Okay, so I'm going to start with a review of something I know y'all already know. Oops. Okay, and technical difficulties. Oh, that's because... There we go. Okay. Suppose I have one of these kinds of functions, such as this one. This is what we'll usually call a single variable function, in the sense that it has one input variable, one output. This is the kind of function that you saw back in high school, most of the kinds of functions that you've seen up until very recently, of course. And again, here's an easy example of such a function. Single number x goes in, single number x plus 1 comes out. So, single variable function. So, what if I wanted to draw the graph of this function? What is the process? Now, I know you all know how to do it. I know you can mechanically do it, but I want to talk about the process. Okay? And the process is, step one, we introduce a new variable into the situation. And we do that by taking the output value of the function, and we choose to set that equal to the value of this new second variable. That's an arbitrary choice. There is no law that says that's what y has to equal. Right? We are choosing to take the output values of this function f. It has one input variable, single variable function of x. We're choosing to call the output value y. That's the first step in the graph construction. Now, if that seems sort of like obligatory, or something that, well, that's just what you're supposed to do, that's a commentary on how ubiquitous and nearly universal the graph construction is in single variable calculus classes, but it will not be in multivariable calculus classes. So it's important at this stage to kind of get used to the idea that this is not always what we're going to be doing. Right? So this is specific and peculiar to the graph construction. Okay, all right, so that being said, once you, so again, you have your single variable function, you set it equal, you set the output values equal to a new variable, in this case y. The graph of the original function is the solution set to this equation. So there's, again, a two-step process when you want to draw a graph and you want to construct a graph. You take the output values of the function, you set it equal to a new variable, typically y. Step two, draw the solution set to that equation. Now, we started with a function. Again, our goal is to draw the graph of this function. Started with a function. Note that an equation is one of the tools, one of the stepping stones in this process of generating this, this graph construction. Make sure to understand the difference between the function, this single variable thing involving only x's, and this equation that we use as part of the graph construction. They're not the same thing. Okay. All right. So now that hopefully that at least the process is familiar. Maybe the emphasis and the point of view I would expect, in fact, to be new to you. But I presume that at least it looks familiar. And so here's an easy example. There's a function. Let's draw the graph of this function. Well, step one, take the output values of the function and set it equal to a new variable. In this case, we're calling it y. Again, very standard. Next step, realize that this equation, and I'm going to rewrite it as that equation just to put it in the more sort of convenient form. This is that standard form. It looks a lot more like n dot x equals n dot x naught. Second step is to draw the solution set to that resulting equation, and here's what that looks like. So that is the graph of this function. Okay, is everybody on board as we see the process? Okay, again, hopefully drawing these single variable graphs is familiar. Now, what does this look like in the multivariable context? So what is it? If I want to draw a graph of a multivariable function, I'm going to show you the general construction and then dial it back just a little bit. So specifically, if you have a multivariable function, as before, as in the single variable case, you create new variables to be set equal to the output values of the function, like so. So we're taking what comes out of the function and setting it equal to new variables. Now I have to say plural because, of course, this function has m different outputs, and so there are m different output variables that have to get set equal to something, and therefore m new such variables. Okay. Now, given the observation that we made a while ago about how you think of multivariable functions, as instead of taking in several numbers, you can think of those numbers as being the coordinates of a vector or a point, if you prefer. So alternatively, instead of writing this, which takes up a lot of space on the page, more compactly, you can just write this. Okay, so let's see an example. Here's a multivariable function. This is a function of two variables. Now let me note, here's the dial it back part. This is a real valued function. There's not a vector output. There's just a single number that comes out. That number is x1 plus x2. It's one number. Okay? So two numbers in, multivariable in, only one number out. This is an easier case to consider. The pictures end up being easier, and almost every example we're going to see of graphs, multivariable graphs, will be such. So real valued outputs, which is nice. Okay, so let's draw the graph of this function. What does that mean? Well, following the process says take the output values of the function, and again, set that equal to new variable. In this case, only one new variable because there's only one output, and therefore we get this equation here. That's step one. That's step two, draw the solution set to this equation. Now, first of all, let's decide now what kind of an object is this. We've got an equation that involves three variables now. Right? There's the two input variables that kind of came along with the function. And then the output value got set equal to a third variable. Grand total, then we have three variables. So this is a function involving three variables. An equation involving three variables, and so we expect this to be a surface of some sort. And then moving the terms around and thinking about the various experiences we've had in the past, we notice that this happens to be the equation of a plane. And did I draw a picture? Yeah, here it is. So here's a picture of the plane that is the graph of this function. Okay. All right. Another example. Here's a function, R2 to R1. So real valued, because the output of this function is just a real number. And here's the formula for how to compute that output value. Question, how do we draw the graph of that function? Well, again, you take the output value of the function, set it equal to a new variable. Now in this case, notice I've already used x and I've already used y as one of the input variables. So I can't set this equal to y. You can't just sort of autopilot and say, oh, y is always my new variable. Your y is previously chosen as an input variable. So heads up on that. Make reasonable decisions as to what to call the output value. If y and or z is available, it's typically a pretty good choice. But make sure to not inadvertently confuse your variables. So here we go. We have an equation now, again involving three variables, x, y, and z now. And we can use techniques from the section on equations that we talked about last time and figure out what this surface looks like. In this case, sadly, it's not a rotation of anything. That's too bad. And that's a nice technique. This is not a sort of a stretched out or translated version of something that we've seen previously. That's a disappointment as well. But we can take cross sections, and if you look at various cross sections, you know, set x equal to various constants, set y equal to various constants, etc., you'll note that the cross sections are parabolas and lines. And there's a bunch of details that I'm going to leave to you guys to check. This would be a great practice problem. I want to encourage you to do this. But take the various cross sections of the solution set to that equation, following, again, the techniques that we talked about last time, and persuade yourself this is what it looks like. It's kind of an angled trough kind of thing. It looks kind of like this. Does that make sense? I mean, can everybody kind of see this coming? In other words, imagine if you were to take this thing and take cross sections. Here, I'll draw it like this. If you were to take cross sections, for example, like that, you can kind of see those cross sections would be parabolas, right? And likewise, if you were to take cross sections like this, those cross sections would be parabolas. But if you were to take a cross section like this, the cross section would be a line. So anyway, think through the details and fill in those blanks. Questions? How's everybody doing so far? All right. Oh. I'm going to skip this next example. You guys can read this one on your own. This last example I do want to talk about. Now here you'll notice the function in question is not real valued. Here the function in question is vector valued. That's another term I'll be using often. Vector valued function to indicate that what comes out is a vector, or said differently, what comes out are multiple different variables. So what's the graph of this function look like? Well, we're not going to give a good answer to that question. In fact, we're not even going to try to draw the graph of this function, because let's think about what the result would be. If I have an equation that involves taking the output values, which are in terms of these two input variables, and setting those outputs equal to themselves, each one of the two of them equal to a new variable, grand total, there's 4 variables. So the graph of this innocent looking little function with a mere 2 inputs and 2 outputs is some sort of a creature that lives in R4. And I just can't begin to draw that. We just can't. Does it make sense? I mean, we don't have the physical experience to be able to visualize something it's just too high dimensional. So the reason I like to show this example is to emphasize that this is one of the big reasons that we don't rely as uniformly in multivariable calculus on the graph construction, because we just can't. Right? In single variable calculus, you never have this problem. In single variable calculus, there's 1 input variable, there's 1 output variable, grand total 2 variables, giving you a 2-dimensional picture that is the perfect problem for a 2-dimensional piece of paper, which is cheap and easily available. And so we can draw graphs effortlessly. I mean, it's no problem. It's the perfect context for drawing graphs. And that's why, what's one of the reasons anyway, that graphs are so uniformly relied upon in single variable calculus classes. Can't do that in multivariate. So, point to keep in mind there. And that's why we're going to go on and look for alternatives, sort of different ways of getting some sort of a picture on the page to represent multivariable functions for which we simply can't draw graphs. So here's the next one. It's called the level set instruction. So now I emphasize we're still interested in a function. So I want to draw a picture of a function. But maybe I can't draw the graph. So I want to come up with a different process that results in a different kind of a picture that maybe in some instances I might actually be able to draw when the graph wouldn't work. Okay, so here's the definition. A level set of a real valued function, and I'm just going to talk about real valued functions here. So specifically real valued because there's a single number that comes out. Is the solution set. So we're looking at the complete set of solutions to, again, a certain equation. And again, we're setting the values of the function equal to something. It's just that we're no longer setting the values of the function equal to a new variable. When we were drawing graphs, we set f of x equal to, like y or z or something. Here, we're setting the values of the function equal to a constant. It is very much not the same construction. This equation is very conspicuously different from the equation that we used to generate the graph construction. So very different. And it's going to result in a very different picture. All right. So firstly, I do want to observe that if you look at this equation and ask, where does this equation live? What kind of a world is this describing here? Notice that the only variables in this equation are the variables which describe the input to the function. Right? So this equation is in a space where the axes, if you will, for this space are just the input variables. Said differently, this equation takes place in the domain. Right? So the level sets that are described here are always in the domain. There's arguably something extremely natural about this. So we started off with, don't forget, and let me zoom in a notch here, a couple notches. We started off with this function, and a function has, among other things, a domain and a target. So the domain in particular is one of the natural spaces that's part of what this function most fundamentally is. Level sets live in that naturally pre-existing space called the domain. Very natural. Now let's talk about the graph construction again, just for a moment. Where does the graph construction live? Well, it lives in a space with axes that involve not just the input variables, but also the output variables. And so it's like we're taking the domain, which is where the input variables come from, and the target, which is where the output variables that would be involved in the graph construction. We're taking all of these, we're taking the domain and the target, and we're kind of bringing them together and put all the variables on the same axis system to create this really fairly unnatural new world. Just so that we can draw the graph construction. So not that we can't do that, it's perfectly fine, we can do it, it generates great pictures in a lot of cases, but I note it's a little unnatural. Level sets, no problem, they're in the domain. Very natural. Okay. Right. So I'll give you a couple of just a quick real world applications of this idea. Functions, as you recall, represent different things. So for example, among many other things you might represent with a function is temperature. Let's suppose just for a moment that we're talking about the temperature. Here, let me do it like this. Suppose that is the temperature function. So for every point in Rn, there's an associated real number that comes out, and I could designate that to be the temperature at that location in Rn. Right. So what would a level set be? A level set then would be the collection of points in the domain where the temperature is a certain fixed constant. And they have a word for this. They call this an isotherm. Iso means same, and therm is suggestive of temperature. So very natural, a little bit of terminology there. And if you are, I'm going to draw some pictures in a minute, but if you're looking at the weather on the news, or online, as might be more commonly these days, and you see these pictures that show various streaks of different colors, and the lines in between, those lines in between are points where the temperature is the same. Those are in fact level sets of the temperature function. They don't call them level sets of the temperature function, they call them isotherms. So be on the lookout for this kind of thing. Likewise, they talk about isobars when they're drawing pictures of barometric pressure. In general, if your function's representing some sort of a quantity, and this comes up in economics, isoquants, because you are literally looking for values where the quantity represented by the function are all the same. Okay. All right, now one more little bit of terminology before I start drawing pictures. I want to motivate this term preimage. I'm going to draw a little picture here. Whoops. So again, here we're looking at a real valued function, and keep in mind some old terminology we have is that if you have an input point, the corresponding output point here, this is called the image. That's the image of the input point. It's what comes out of the function given that input. So what we're doing with the level set construction here is kind of the opposite of that in some sense. In the level set construction, we're picking an output, and we're kind of coming back here to look for all of the input points, all the points in the domain x, such that when you put them into the function, you get this c out. So given a c here, this is that level set, and given that you're kind of going in some sense backwards through the function, instead of calling this c is the image, this then gets called the preimage. And it's just sort of suggestive of the fact that you're sort of moving backwards through the function. That motivates this notation, f inverse of c. It's a little bit sloppy notation in some sense. This makes it look like the function's invertible. Probably isn't. But in particular, it's indicative that we're taking an output value and moving backwards through the function to get corresponding input values. Okay, so the notation's very common, and the terminology is also not rare. So be on the lookout for that terminology, preimage, and that notation. Okay, so let's see an example. Here is a function. We drew the graph of this function previously. The graph you get by taking this output, x1 plus x2, and setting it equal to a new variable, a third variable, y, thus giving you a three-variable equation, and thus what ends up being a plane. Okay. Not what we're going to do here. Here, for the level set construction, we're going to be taking the output values of the function and setting equal to various different constants. Note that for each one of these, where we set it equal to a constant, we get an equation that involves only two variables. So there's no R3 in play here, nor should there really be. Look at this, the domain's two-dimensional. Right? Why would we talk about R3 if the domain's two-dimensional? So equations of two variables. Furthermore, in this case, I can look at each of these equations of two variables and conveniently recognize they're all lines. And you get different lines depending on what that c is that you're setting it equal to. And each one is a line with slope -1. In fact, here's your picture. Right? All of those level sets, all of those preimages are lines in the x1, x2 plane of slope -1. And this is what happens. This line right here is what you get when, highlight. This is the line that you get when you set x equal to, when you set f equal to 0. Thus we call it f inverse of 0, et cetera, et cetera. This is what you get when you set f equal to 1. This is what you get when you set f equal to 2, etc. Okay. Now let me go ahead and jump in and draw the weather picture. So I'm going to draw a function of two variables here. So now again, I'm drawing the domain, and I'm going to make a sad little attempt here to draw the United States, because this is what they typically draw weather maps of. And now, what do these weather temperature functions look like? Well, they usually have like a blue line up here indicating where it's really cold, and then it starts to turn more toward the red side of the spectrum as you go further down. All right, and they'll put various different numbers on here. Maybe this is 40 and 50 and 60, and then maybe 70, and now it's getting warmer, and down here it's 80. So we've all seen pictures like this on the news, on the satellite images on the internet, etc. And in fact, what they are is level sets. Right? This curve here, this yellow curve, that is a level set of the temperature function. That is the curve showing where in the domain, namely where on the map, is the temperature exactly equal to 60. And then you can kind of infer, seeing all these different level sets, you sort of fill in the blank and you say, okay, well, let's see, where are we? We are currently about there. So, and let's see, there's the 50 line, there's the 60 line, and even though I don't see exactly what the temperature is here, I don't know, I'm going to guess about 57 or something. Right? So it's not perfect. It doesn't communicate everything that there is to say about the function in question, but you get a picture, and it's kind of geometrically relatable. Okay. How are we doing? Is everybody on board? Okay, turns out there is a relationship between level sets and graphs. Now, this is not immediately clear. I would go so far as to say even kind of unexpected, because remember, I made a big deal out of the fact this is a very different construction. Right? The graph construction says you take your function, you set it equal to a new variable, and you deal with that equation. The level set construction, you take your function and you don't set it equal to a new variable, you set it equal to a constant, or various different constants, and then you get these very different equations. So, and thus very different pictures. But there is a connection, and here's the idea. Again, the graph is formed by setting the function equal to a new variable. Level sets are formed by setting the function equal to a constant. Well, if I were to set the function equal to z, and then subsequently if I were to set z equal to c, let's look at what we have in blue here. If f is equal to z and if z is equal to c, altogether f is being set equal to c. All right, now let's say that what I just said here, let's say that same thing in geometric language. If I form the graph of a function, and then subsequently if I look at a horizontal cross-section, and keep in mind the plane z equals c is a horizontal cross-section. If I look at a graph and then take a horizontal cross-section of that graph, I get a level set, which is what I would have gotten if I had just set f equal to c in the first place. Okay, so now let's see a picture of what that looks like. Here's a kind of a picture. Got some function f. If I set f equal to z, that gives me this graph surface. If I then set z equal to c, namely if I take this horizontal plane, this horizontal cross-section, z equals c and z equals f together, namely the horizontal cross-section of that graph, gives me that curve, which is exactly what I would have gotten if I had just set z equal to c in the first, excuse me, f equal to c in the first place. How are we doing? Does everybody see the observation there? So it's on the algebraic side, it's kind of a silly observation. If z equals c, then f equals z is the same as f equals c, right? And geometrically, we get this really nice connection between graphs and level sets. So level sets are horizontal cross sections of graphs. Now, asterisk, ever so slight awkwardness. Technically, this cross section is, yeah, it's a curve. Yeah, it looks just like this level set curve, but technically this is a curve in R3. All the points on this cross section curve take place at an altitude, you know, where z equals c, and these points set down here that are level sets don't have altitudes. These are just points in the xy plane. So technically not quite the same, but the point is that this cross-section curve and this level set curve have the same shape in that they're just, the relationship between x and y, the x and y shapes are the same. So sloppily we'll say that they're the same. All right, so neat fact there. Let's see an example. Yeah, I'm going to just go back to where the example is. These, get rid of that mess. These lines here, these were level sets that we drew. We drew various level sets. They were level sets of a certain function. They were level sets of this function. But remember, we drew the graph of that function some time ago. Right? One of the very first things we did today is draw the graph. So what did that graph look like? Well, that graph was this. Right? In fact, I appeal to your geometric intuition. If you were to take cross sections, horizontal cross sections of this plane, and this is a hard picture to draw well because this is a plane that's kind of coming up out of the page at us. But the horizontal cross sections would be lines like that, which, if you were to view them down here in the xy plane, would be like that. In other words, the horizontal cross sections of that plane are these lines. Okay, here's another example. I passed it up. There we go. Nope, sorry. There we go. So let's look at and let's zoom back in. Let's look at this function. Can I draw level sets of this function? Well, sure. Level sets of that function, you take the value of the function, you set it equal to a constant to form the level sets. That's what a level set is. Right? And you get these equations, and we happily observe that these equations are familiar. These are the equations of circles in Algebra 2 class, right? A long time ago. But so we get these circles. Now, does that relate to the graph? Well, sure. In fact, remember the graph of this function is what you get when you set this equal to a new variable z. And we drew that graph. That graph was a paraboloid. And in particular, these circular cross sections drawn there, those circular cross sections are the horizontal cross sections of this graph that we drew a while ago for the same function. Let's take a horizontal cross section of that paraboloid and you get these circles. Okay, so let's do a little compare and contrast now. We have these two different options for how to represent a function geometrically. Keep in mind our goal here. We've got a function, an algebraic object, a function. I want to draw some sort of a picture to get some sense, some geometric intuition for what the function kind of looks like. I have the graph construction, it's very familiar. Now I have this level set construction. They produce different, though related, pictures, but different pictures. What are the pros and cons? Okay, so I'm going to talk about the advantages of level set construction because, again, graphs are very familiar. Students love graphs. almost cling to graphs. So what's the advantage? Well, there's a huge dimensional advantage that's worth observing. So specifically, if you have a function from R2 to R1, we just looked at a couple of these actually, drawing graphs of pictures like this produces pictures that are three-dimensional. They're hard to draw. You got to do the perspective thing and try to on a two-dimensional piece of paper make your viewer visualize a three-dimensional world. It's actually kind of challenging, right? Level sets are two-dimensional. Level sets take place in the domain. Two-dimensional, we have two-dimensional paper. Even better than that, the level sets are one-dimensional curves. That's what pencils produce. You can draw a one-dimensional curve with a pencil. Going back to graphs, can you really draw a two-dimensional surface? Well, not really. The pencil draws a curve that you use to try to conjure the image of a two-dimensional surface, but you draw like the horizons and the corners and the edges, and you don't really draw the surface. Right? Let me just again point out. Kind of appealing to your imagination that there is a surface here. One could argue that this is just a loop with a piece of string dangling from it. Right? And I have to appeal to your intuition to imagine that there's actually stuff here. I didn't draw it. So awkward, right? Geometrically, it's kind of awkward. So the dimensional advantages are very nice for the level set construction. I'm going to show another such example in a minute. Here it is. So let's look at this function where f is x squared plus y squared plus z squared. Note this is from R3 to R1. And let's think about our various options for how to represent this function. Maybe we should try to draw the graph. But you can't. Look at how many variables there are. 3 inputs, 1 output, altogether 4 variables. The graph of this function, this not very scary looking function, the graph lives in a 4-dimensional space that I couldn't begin to represent, much less draw whatever the graph of that thing would look like. So highly unsatisfactory. On the other hand, the level sets, I can draw those. I mean, it's a stretch. It's at the upper limit of my dimensional capabilities, but that's a sphere. Right? And I can draw spheres. So it's this or nothing. Right? And the level set wins in this situation. It's a picture. It's not everything there is to know about the function. There's this big gap in between. I've only drawn 2 of the spheres. I guess I could have drawn 3, maybe 4 or something. So I'm drawing just a few, in some sense, cross sections of the graph that ideally I would like to draw. But at least I can draw something. All right. Next observation I want to point out. Any equation, the solution set to any equation. It's a big tent, right? Lots of different equations, lots of reasons we might be interested in equations. Any equation solution set, I can view it as a level set of some function. And it's a really easy observation to make. I've kind of made this observation before, that if you have an equation, you know, stuff equals stuff, you can take that stuff, move it over to the other side, and you get stuff equals 0. Right? So that is a level set of that function. And it's just, you can always do this because that's how equations work. Equations, whatever you have on the right, you can move it over to the left with the minus sign, and you end up with stuff equals a constant. So what's valuable about this, why this makes it important to study level sets, and one of the things we're going to do in this course a little bit later on, very soon actually, is talk about what are the relationships between level sets, the geometric features of level sets, and the calculus of the function in question, that you can compute algebraically. And what we're going to find is there's some pretty strong connections there. So in particular, whenever you have an equation, if you reinterpret it as a level set of some function, and if you understand how what the connections are between level sets and algebraic calculations of calculus, then you can use calculus to understand the solution set to any equations, at least in some certain ways. So that's a really neat trick. Level sets are awesome in this sense, and I observe you cannot say the same thing about graphs. Not every equation can be viewed as the graph of some function. Take this one here, for example. It's not the graph of anything. This fails the vertical line test. And this is an ellipse, sort of a shifted ellipse. Flashbacks to Algebra 2 class. Fails the vertical line test. So you can't use your knowledge of graphs and how graphs relate to calculus to use calculus to understand this thing. Right? You have to use level sets. Okay. Right, and that's this example here. All graphs can be viewed as level sets. This is really just a special case of our previous observation. Every graph in particular is described with an equation, and then all equations can be viewed as level sets. So here's how the algebra of this observation works out. This is important algebra to make sure you're comfortable with. Suppose you have a function f. The way you form the graph of that function is to take the output values of the function and set them equal to a new variable. So this forms the graph of that function. All right, so given a function, the graph is described by a certain equation. Now, can I view this as a level set of something? Is this equation the level set of some function? Well, it's certainly not the level set of f. Right, the level set of f, or a level set of f, would be described by f equaling a constant. Y is not a constant. But I can play this trick that we talked about. I can take this and move it over to the other side of the equation, like so. And note what I have then is stuff equals a constant. So that stuff that's being set equal to a constant, that is the function. It's a new function. It's not f. See? It's y minus f. But that's a new function which is being set equal to 0. Namely, this is a new function whose level set is the graph of f. Everybody see how that little slick move works? This is a surprisingly useful it almost seems like nothing happened. In some sense, algebraically speaking anyway, it looks like, well, I just subtracted this over to the other side of the equation. Who cares? The reason we care is that that allows us to reinterpret what we had originally conceived of as a graph as a level set. And we're going to draw some powerful conclusions about how level sets relate to calculus, and therefore I'm going to be able to do certain really nifty things. Anytime I'm looking at a graph, this algebra will help me find the new function g, and then I can use the calculus of level sets to draw certain conclusions. And the details of that, again, will come in a few days, I guess probably next week now that I think about it. Okay. There are several exercises in this section. I guess, well, I do have one more. No, that's it. There's several exercises in this section. A lot of what is important in this section is not so much the process of doing complex, intricate algebraic manipulations and that kind of thing. A lot of what's important about this and the last section is understanding the language, right? Being able to make proper use of the word graph, the word level set, the word equation, right? And so think that through very carefully and make sure that you get the, it's going to sound sad, but make sure you get the grammar right, because being able to communicate about these related but importantly different things accurately is essential to being able to manipulate them and use their features, their capabilities effectively, meaningfully. So focus, think about the language in these sections. Okay. All right. So yeah, moving along. Now here's a third way to represent functions. Geometrically, this is a little bit backwards. we're going to take this the other way. I'm going to talk about, suppose you're given a function. Ask, what is the, well, okay. So I'm going to define something called the image of a function. So the image of a function, now here's your function. Notice the function has a domain and it has a target. So critically, this function here, the domain is not all of Rn. Here I'm talking about the domain as being a subset of Rn. It might be all of Rn, I suppose. Nothing wrong with that. But it need not be. So it might just be some sort of a domain, maybe a solid rectangle or a disk or something like that sitting inside of Rn. Okay. And then there are m different output values, so this is a vector value function. So the image of this function is a subset of Rm. Specifically, the image is just the actual output values. What actually comes out of the function. The values f of x are the image. Specifically, it's the f of x's where those x's actually are in the domain. So specifically, it is actual output values that come from the domain of the function. Now, what's the difference? How is this not just the target? Well, importantly, the target is just a space where the outputs are required to land. Not everything in the target will necessarily come out of this function. Right? So the target is just a context, really. It's I need to tell you what kind of critters are coming out of this function. The image is the actual outputs themselves. Okay. All right. All right. So let's talk about it. Let me show you an example of an image. I guess I'll zoom in here. Okay, so suppose I have a function from R1 to R2, and I'm going to draw the domain over there, and then the function is doing something, and then here's the target. There's my function from R1 to R2. Now, what does the image of this function look like? Well, let me just kind of plot some examples. This input value from R1 is going to have some sort of an output point there in R2. This input point is going to have, I don't know, this is a nearby input. Presumably, hopefully, if it's a nice function, there will be some nearby output. Nearby input, nearby output. Nearby input, nearby output. Let's see, I'll draw one more. Nearby input, nearby output. Okay, so the idea here then is that this function is kind of, it's taking, as I sort of move along in the domain, you'll notice I'm kind of creating a little curve in R2 in the output. So images are typically of the same dimension as the domain. Typically, not always, plenty of counterexamples. But this is sort of what you expect. In other words, keeping in mind that what the function does is it takes input points and gives output points. It's effectively taking the entire domain, picking it up, and maybe bending it around, contorting it in some way, but then placing it down in the target. So typically, if you have a function of one variable, you expect the image to be one-dimensional, in this case a curve. All right, so this curve here is the image of this function. All right. Now I say this is backwards because this is grammatically not how we usually talk about these kinds of things. Usually we talk about, suppose you give me a curve, what is the corresponding function? And this is where the term parameterization comes up. A parameterization of a curve, so you start with a curve. A parameterization is moving backwards through this process and finding the function whose image is that curve. Okay, so that's called a parameterization. Yeah, here we go. Function whose image is a curve is a parameterization of that curve. Okay. Now a technical terminological point. Once you have not just a curve, but once you have a parameterization of that curve, the pair, which is the curve and the parameterization together, we call that then a parametric curve. So this is a pair. A parametric curve is not just a curve. It's not just a set of points that just sits there inert. Right? A parametric curve is that set of points with the understanding that it is paired with a certain function whose image is that curve. So it's both of them together. Okay, and likewise, if you can parameterize a surface, and we'll talk about that in a few minutes, if you can parameterize a surface, then the pair, the parameterization and the surface together, together, we call that a parametric surface. Okay. All right, so let me show you some examples. Suppose I have this function here. Note that's a function from R1 to R2. So a single number goes in. I'm using t as the input number here. We'll talk about why I choose t in a few minutes. And then out comes a point. You'll notice it comes out here as both an x-coordinate and a y-coordinate. So let's try to figure out what the image of this function looks like. What kind of a thing is this? I mean, I figure it's got a single input, so it's probably a curve. I'm expecting it to be a curve because it's one-dimensional. It's going to live inside of R2. It itself is going to be a one-dimensional thing. How would I know what curve it is? And here's the way, or a way to try to figure this out. Realize that the first coordinate there is, in fact, the x-coordinate, and the second coordinate is the y-coordinate. Right, so when you parameterize, you're writing down a formula for the x-coordinate and the y-coordinate. So you have formulas for these individual coordinates. If you can find a relationship between these algebraic expressions, if you can find a relationship between, in this case, t plus 1 and 2t minus 1, what you have found is an algebraic relationship between x and y. Namely, you will have found an equation that relates to the curve in question. And that's exactly what we're going to do. I'm going to just observe that by a little bit of algebraic manipulation, I can figure out what I have to do to t plus 1 to get it to turn into 2t minus 1. And here's just how that sort of a dumb attempt goes. If I take t plus 1, if I want to try to make this look like 2t minus 1, well, I guess the first thing I would do is multiply both sides by 2. Now I have 2t plus 2. I don't want 2t plus 2. I want 2t minus 1. So now let's subtract 3 from it, and this is that. So y is 2x minus 3. Everybody see what happened there? You just think of, now this particular process of taking the x and manipulating it to try to make it look more like the y is one way to get there, but the punchline is you're looking for, just given the formulas that you have that are, in fact, the x and the y, you just want to find some sort of an algebraic relationship between these formulas, because that's an algebraic relationship between y and x. So now what do I conclude from this? Well, what I can conclude in this case, because this gives me that relation, every point that comes out of this parameterization, every output from this function, every point on the image that I'm trying to deduce, satisfies this equation. This is the equation of a line, right? Algebra 1 fact from way back when. So that means that this entire image, the image of this thing, it's all on this line. And it's tempting to say, well, it is the line. And in fact, that's true in this case, but it doesn't quite follow. All I've really shown is that this image is a subset of that line. Okay. Now, is it the whole line? Well, we don't really know that yet. All we know for sure is that it's on the line. Is it necessarily the entire line? Well, yeah, here's how you know in this case. If you would like to know that this traces out the entire line, then give me a point on the line and I'm going to show you that I can construct that point. I can get that point, this exact point, to come out of this function. And the way I'm going to do it is by observing that this point, there's only one point on the line that has this value of x naught. Given that value of x naught, given that value of x naught, if that is going to be produced by this expression, I can solve for t. T is x minus 1, so this then is the value of t that I would expect to produce that value x naught and therefore this point on the line. And then you can just confirm that this actually works. It's sort of a brute force. Let's take this value of t and let's see what does that value of t, what comes out of the function when you put in that value of t. Well, let's see here. Here's the formula for the function. T naught is x naught minus 1. And then simplify this expression, and it turns out to be conveniently exactly x naught y naught. Okay, so not only is every point on this image on this line, but furthermore, the image creates the entire line. Okay, so that's how this process works. Given a function, how to find the image, or at least this is an example of it. Sadly, it won't always be exactly like this. Sometimes the way you find the algebraic relationship is different. Sometimes you can't find an immediate algebraic relationship between all the variables and you have to try different things, and I'll show you some examples of those. Okay. Yeah. Here's another example. Let's look at this function. Also from R1 to R2. So again, we are sort of expecting a one-dimensional curve in R2, so in the xy plane or a two-dimensional plane. Okay. And again, what can I do? Well, I guess I'll take the x and the y and I'll try to figure out what can I do to this expression giving me x that would allow me to result in y, thus giving me an algebraic relationship between them. And what's weird is it's exactly the same thing. This is very unexpected, but this y, just like the last example, this y is exactly 2 times this x minus 3. And again, you can always find a value of t that will generate any specific given point, whatever point on this line you might happen to be interested in. So weirdly, this very different function here, I mean, it's cubic, right? It's a very different function, and yet its image is the exact same line as the line from the previous example. That's disturbing and unsettling. It's one of the significant limitations of using images to represent functions is because there's different functions that have the same corresponding picture. That's too bad. I'm going to come back to that disappointment in a few seconds. I want to reinterpret now, though. First, why do I choose t as the variable? What we call the parameter for these parameterizations. And again, you don't have to, and sometimes, in fact, you don't. But what the motivation for using t is that you can think of t, this parameter, as representing time. Right? Note, if you do so, then you are interpreting position, that's a location, as a function of time. That is a familiar physical concept, thinking of position as a function of time. In other words, movement of a particle through space, or through the xy plane. That's something we can all kind of relate to. Right? So along those lines, we can think of a parameterization as describing a movement, a sort of a process. I like to start with the snail example. So suppose you have a snail, and if you know where in x and y coordinates the snail is at any given moment in time, then you know exactly what the snail is doing. Namely, maybe the snail started here, and then as time passed, in other words, as the parameter t increases, his position changes, and altogether you have a representation of his movement. Okay. So, interestingly though, I will point out that the curve, that is the image of this function, is not the same as the function. So there's a really critically different, there's a missing piece of information, there's a missing sort of story here. If I just look at, by the way, I don't know if y'all, depending on what part of the country you're from, but if snails crawl along the sidewalk, they leave this little trail of slime. Right? So the trail of slime, that is the curve, that is the image of his position function. Not the whole story. Right? If you look down on the sidewalk and see a trail of slime, you know that the snail crawled along that trail, but you don't know when. You don't know, was he moving like really fast at the beginning and then he slowed down in the curve to avoid falling over, and then he sped up again and then he slowed down in the curve again, right? It's possible. Or was he going uniform constant speed the entire time? Right? Could be either. So the image construction leaves out the story of how it came to, how this image was created. Right? All you see is the result. You don't see the process. Okay. Related metaphor, one of my favorite metaphors for this, is to distinguish between the road and the road trip. Right? So in other words, if you say let's jump onto I-40 and drive to Wilmington, right? If you do that, the road is just sitting there. Right? If I were to talk about our position function, position as a function of time, we're on I-40, and that's been there for many years, and presumably will be for many years from now. The road trip is this much more detailed. There's a lot more information in the road trip, namely how fast was I going, where did I start, did I accelerate and then decelerate and maybe come to a stop, get a drink of water, get back on the road, start driving again. There's a whole process there. So the road is just a set of points. The road trip is the whole story of exactly where I was, exactly when, throughout the entire process. And so that's the difference between the image and the parameterization. The image is the road, the parameterization is the road trip. Okay. All right. That being said, here's kind of a way I can adjust my figure. You remember, this is the first function that we looked at. This is the second function that we looked at, and we were disturbed to note that their images are the same line. Two very different functions. But the images are the same line, y equals, 2x minus 3, I guess. So, sure, fine. Well, you can, per our previous observations, you can note that what's missing from the road, what's missing from the image is the documentation of where I was when. But you could, it's not perfect, it's not thorough, but you could put little landmarks and say, okay, yeah, but for this experience here, for this road trip here, when t was -1, I was at that location. When t was -0.5, I was at that location. And you can just document certain places that you were at certain times. Whereas for this different parameterization, this different road trip, yeah, same road. I'm still driving on the road. but I was at different places at different times. That make sense to everybody? Okay. All right, so on the first one, said differently, and I'm just going to appeal to your physical intuition here. We were going at a constant speed. We'll make that precise in a little while, talk about how to compute speed and how a parametric curve relates to velocity. There's a little story that has to be told. Here, I appeal again, loosely, to your geometric intuition. I was moving faster here at the beginning, and then I kind of slowed down. In fact, you might even be able to sort of speculate. In fact, we came to a stop at t equals 0 momentarily, and then we started accelerating again. So this was a kind of like that, as opposed to that there. Okay, so see some more examples. I'm going to do this one very quickly because this is an easy one. Function from R1 to R3, so a curve in 3 space. And there's a couple of quick observations that you can make. You can notice that x and y are easily related. And you can notice that x and z are easily related. They're all multiples of e to the t, so easy observations to make. Therefore, the image, what I'm looking for, is on the intersection of these two surfaces, whatever those are, and then you realize, oh, wait a minute, well, those are, in fact, planes. So back from chapter 1, right? These are equations of planes in R3, and so you can ask them, what happens when you take two planes and look at the intersection of those two planes? Well, you get a line. In fact, you could use observations much like these to generate the symmetric equation of the line that is parametrized by this function. Okay, now, is it the whole line? Well, again, that doesn't follow. All I've observed is that every point on this image is on this line because it satisfies these equations. In fact, here it does not generate the whole line. In fact, you'll note here x, y, and z are always positive. Easy observation, right? The line goes infinitely in both directions. The image never goes to or beyond the origin in the negative direction. So just keep in mind, weirdo stuff happens sometimes. Not every image is sort of the whole equation that you might deduce. Okay. All right, another example. Curve in the xy plane. Here's the function. Here, instead of taking the x and trying to manipulate it around to get the y, an easier thing to do is just observe. It's kind of use your instinct, your memory of trig identities to note that this x and this y have an existing relation between them. Namely, there is this Pythagorean relation between cosine and sine, and therefore this x and this y have this relationship. X squared plus y squared is equal to 1. And what that tells you immediately is that this function, its image is a subset of that circle, that unit circle. Now, is it the whole circle? Well, again, you have to sort of think it through and confirm that it actually does trace out the whole circle. And that's not a hard problem. You can persuade yourself that for various values of t, you generate various parts of this curve. And I'll let you guys read that part of the example on your own. So the punchline is yes, and so this is a parameterization. This function is a parameterization of that unit circle. All right. What about this function? Now, note that this is a curve in R3. How can I figure out what this looks like? Well, in fact, looking at the three different coordinates here, looking at the x and the y and the z, No particular relationship really leaps to mind between that relates all three of these. So that's awkward, right? We can't really use the technique we did previously. What I'm going to do here is take a different sort of approach, trying to get a handle on what does the image of this function look like. Said differently, what curve does this function parameterize? The way I'm going to do this is by looking at this sort of one bit at a time. I'm going to start off looking at just the x and y coordinates. We'll worry about z later. Okay. So I don't know what the curve looks like. I just want to know what does the projection of this curve look like down in the xy plane. And conveniently, in the xy plane, looking only at the x and y coordinates, I see the cosine and the sine again. That's our old friend from our last example. And it's not hard to persuade yourself that that then is tracing out the unit circle in the xy plane. Now, geometrically, what does that mean? That if I were to throw away the z coordinate, that I would get a circle. What that means is that the actual point in question that's moving along, the actual point in question, its projection into the xy plane, which is exactly what you get when you throw away the z coordinate, that just says let's just smash it down into the xy plane. That projection into the xy plane is this circle. So what I deduce from this observation is that whatever the curve might be doing, the shadow, the noon shadow, when the sun's straight overhead, that projection down into the xy plane is doing this. It's making a circle, going counterclockwise. Okay. Now, not the whole story. That's really not enough information. Now I got to think about what's going on with the z coordinate. And here I'm just going to observe that the z coordinate is t, and so as time passes, as t increases, z increases. So using these two pieces of information together, and I appeal to your geometric intuition, we're looking for a curve whose shadow is doing this, and that's rising at constant speed. And I appeal to your geometric intuition. That makes a helix. That makes this curve there. So notice the altitude is increasing at a constant rate, but the projection is sitting here running around in a circle. Sometimes you have to do stuff like that. Okay. Here's another example. Again, a little different. Not like the last one. We're going to use a different technique here to try to understand what this parameterizes. So what's the image of this function? Again, it's you see a semblance between the x and the y functions, but they're not exactly the same. It's not clear what you do with this. The easy thing to do here is to break it down like this, and notice that that is an easy to describe vector. T comma t, no problem. X and y are both increasing at constant speed. That's easy to draw a picture of. This is easy to draw a picture of. That's just a constant vector pointing that way. Okay. So all together then, I can kind of group them together, and it says that, look, this is a moving point that's moving in space, like so, moving along like that, and this is always pointing in that -1, 1 direction, but the amount that it is moving in that direction, the amount that that vector points in that direction is being manipulated. We're multiplying it by sine t. So as time moves along, sure, we're always pointing that way, but sometimes more, sometimes less, sometimes negative, sometimes back to 0, etc. And the amount that we point in that direction is adjusted by sine t. So the purple is moving along that ray to the upper right. The green is being added to that, is then deviating in the perpendicular direction by an oscillating amount, and altogether this parameterizes that curve. Now, this is a very different analysis, right, than what we did in the earlier examples. This is just another tool for your, There's no magic formula that says, which technique do you apply to which examples. You just have to keep in mind what are your various different capabilities and tricks that you can pull, and whatever the example is, try to piece it together using these various different tools at your disposal. Okay. All right. Let me just, oh gosh, wait a minute. Okay, so we're not going to finish this section today, sadly. All right, well, we'll draw the line right here, and we'll finish this section tomorrow. Okay, see you guys later.